to start. Make sure my connection's working here. All right. So, a couple words that I'm sure you've heard before, but you may not know how they're defined in the way that we define them as scientists. And those words are law and theory. All right, you've certainly heard of scientific laws before, you've certainly heard of scientific theories before, but what gets confusing is that these words are also used in non-scientific contexts, and so like we get confused about what that means. So for instance, law, there's a very specific definition for what we call a scientific law, and it is a brief statement that summarizes observations and can be used to predict future ones. So you keep noticing that a thing is happening over and over and over and over and over and over and over again. So you kind of summarize those observations into a law, and then that helps predict what's going to happen in the future. So for instance, when we talk about gases in a little bit, we're going to talk about a law that says that the pressure and the volume of a gas are inversely proportional. Because every time you increase the pressure of a gas, the volume goes down. If you increase the volume of a gas, the pressure goes down. So we keep kind of seeing this inverse relationship happen over and over again, and so we like summarize that into a law. All right, notice what it doesn't say there. It doesn't say anything about how true it is or how accurate it is. It doesn't say that it always has to be true under all circumstances. There may be different places where the law holds and where it doesn't hold. And that's very different from our like more popular understanding of law, which is like something like a rule that you have to follow that you can't violate, which is like the public, like our laws as a country or something like that. So then, if that's a law, what's a theory? Yeah. The theory is kind of the what's happening to cause these observations. So the law just summarizes these observations. It says, when this happens, this happens. When this happens, this happens. When this happens, this happens. It doesn't tell us anything about why or what's causing that. So the theory is this is kind of paraphrasing it, but basically explains why things happen. So the law is the summary of the observations. The theory is why that happens. All right. So both of those have to be supported by evidence. You have to have evidential support that shows that this is true. Then if you get enough support in counter to it, you can disprove either of those things also. You can also, over time, we often have to either narrow or expand the definitions or the situations where they apply. But the biggest misconception I think that people have coming into this is the degree to which one is true versus the other. So there's this popular misconception that a law is a thing that is absolutely true and a theory is a thing that is like, we're not sure yet. Have you heard that before? You kind of heard those sorts of definitions, people saying that like a theory is like when you first start thinking about something, and then once you get it like enough evidence, then it becomes a law. That's not how it works. That's mixing up our definitions of theories and laws in the scientific context with like government laws, where you debate ideas and you make a bill and whatever, and then eventually it becomes a law. Those are two completely different things, even though they're using some of the same words. So just if you think of some examples, it can help keep that stuff straight. So one I think about that we're going to talk about next week, a theory is atomic theory, the theory that matter is made out of atoms. So why is that a theory? Yeah.
When things, for example, heat up or cool down, that has to do with atoms. We're trying to explain
Yeah.
what's going on.
Yeah, so like you need atoms to explain how matter interacts with each other. Chemistry only works if we assume that matter is made up of these atoms, and then they do these things and they rearrange themselves and all that stuff. Can we actually visually see atoms? Not really. We have evidence now, we have really good evidence that atoms exist because of things like electron microscopes, scanning tunneling microscopes, things like that. So you've probably seen pictures where it says like here's a picture of an atom or a picture of a molecule. So we can get evidence of that. That's still not like the same thing as being able to see it. So it still is this idea that we're assuming matter is made of atoms, and then that allows us to explain all these different effects. Is that a controversial theory? Are there a lot of people in the world saying like, no, matter is not made of atoms? What do you think? Controversial or no? Yeah, I mean these days probably it's controversial. I always think of it as completely non-controversial. Everybody just is fine with the idea that matter is made out of atoms. If you poke around the internet long enough, you'll probably find some non-atom conspiracy theorists or something out there talking about how they're made of something else. But yeah, it's pretty non-controversial. So that's a good counterexample to this idea that a theory is like just an idea that may or may not be true. That's not really how it works. Atomic theory is well accepted. It explains everything that we do in chemistry. We have plenty of evidence for it. It's a theory because of how it works, because it explains things that happen. So try to keep those straight. That may be a little bit different from how you've thought about those things in the past. Any questions about that? All right. So now that we kind of talk about atomic theory and that kind of stuff, let's talk about matter. There are two different ways we can classify matter. One is by state. So that's probably the easiest one that you've heard before. Whoops. So we can say that matter is a state, solid, liquid, gas. That's called states of matter. We can also classify matter according to its composition, so its components. What is it made out of? So we'll make a little flowchart type thing here. All matter can be split into two different categories. We have pure substances and mixtures. That's a pretty, that makes sense, right? That kind of a separation. Either something is pure or it's a mixture of pure things. Okay, so we can then break it down one step further, and this is where it can get a little bit trickier, because when we think of pure substances, we kind of have to define what that means, and we'll talk about that in a second, because there's actually two different categories of pure substances. There are elements and compounds. And it may help if we look at some examples. So elements are only made of one type of atom. So that would be things that we find on the periodic table, like pure aluminum, for example, is an element. Things like oxygen gas is an element. Carbon is an element. Bromine is a liquid, is an element. It's Br2, it's a diatomic element. So these are substances that are only made of one type of atom. And they're pure substances. They're probably the most obviously pure substances. The one that sometimes gives people a little bit of trouble is the next category, compounds. How would you define compounds? What is something that is pure substance but not an element? What's going on in that substance? Any ideas? Yeah. Yeah, so this is going to be something that is made from two or more elements. So let's say water is a compound. Something like salt, NaCl, is a compound. Sugars like glucose, C6H12O6, compound. So these can get quite big also. So how, if they're made of more than one element, more than one type of atom, why are they still pure substances? Why are they not mixtures? What's special about those types of substances that still makes them pure and not mixtures? Yeah.
They're not mixed with other compounds, it's just them. It's like when you think of water, it's just H2O compounds without anything in between.
You're right. That is just, water is just H2O compounds. But why do we not call that? Why is that different from a mixture of hydrogen and oxygen? What's special about water? Let's just stick with that example. What's special about water, H2O, that where we would say it is not appropriate to say that water is a mixture of hydrogen and oxygen? What's different there? Yeah. Yeah, it actually has to do with how we can separate it. So compounds are combinations of different elements, but they're combined in a chemical way. They're actually bound together by something called a chemical bond, which we'll talk about a little bit later. But we can say here that compounds are only separable. Sorry, I always misspell separate. Only separable by chemical changes. So if we can't physically separate those, we can only chemically separate them. If you have water, you can't physically separate the hydrogen and the oxygen. If you separate the hydrogen and the oxygen from water, you form different new compounds, which makes it a chemical change. So that's the key to understanding why compounds are pure substances and not mixtures. Their components are chemically bound together, and so if you separate them, you have to separate them chemically rather than physically. All right, let's move over to the other side then. There are also two types of mixtures. But while we're thinking about that, let's just make a note here that all mixtures can be physically separated. Right? So you can separate the components of a mixture from each other without changing the identity of any of those compounds, without making new compounds or elements or substances at all. You're not making anything new. You can combine things. You can take them back apart without making anything new, without changing what they are. All right, so the two types of mixtures are homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are sometimes called solutions. And that is where the components of the mixture are so small and so kind of intimately combined that you can't tell different parts of the mixture apart. So they look the same throughout. And there's a little bit of a it's not a super strict definition. Depending on how you look at something, it might appear homogeneous or heterogeneous, like depending on how closely you look at something. So it's not necessarily always a fixed definition, but there are some things that fit well in these categories and are pretty obvious. So like, what's an example of a homogeneous mixture? Something that kind of looks the same throughout. What would you say? Go ahead. You can. I'll take a couple. Go ahead. Kool-Aid. Good. Yeah. Go ahead. Saline. Yep. So sodium chloride solution. So let's write those down here. Kool-Aid. Saline solution, which is a mixture of sodium chloride and water. Kool-Aid is a mixture of a whole bunch of things, right? You got colors, you got flavors, sugar, hopefully, and water. Other homogeneous mixtures? How about some non-liquid homogeneous mixtures? I think of. Yeah, Raj. No. Okay. Anybody else? Non-liquid homogeneous mixtures. Air. Yeah, that's a good one. So air is a mixture of primarily nitrogen, oxygen, water vapor, carbon dioxide, and some other trace gases. And it's a homogeneous mixture, even though everything's invisible. It's homogeneous because we don't have like the oxygen over here and the nitrogen over here and the carbon dioxide over here. Right? There's not like domains of these different things. It's all mixed together evenly, uniformly. Yep. What about a solid homogeneous mixture? These are maybe a little trickier. Ideas?
Non-pure gold.
Yeah, non-pure gold. So maybe like 14 karat gold. Have you heard of like the different karat gold? You know what pure gold is? 24, right? Like the song. So if you have 14 karat gold, now you have less purity in that gold. So it's alloyed with silver and some other stuff to bring down the amount of gold that's in there. And anybody know why they do that? There's actually a couple of reasons.
When you think above 18 karat, it's no longer like durable, so the necklaces that you wear like.
Yeah, that's one reason. Is gold is a very soft metal. So if you actually made like jewelry or whatever out of pure 24 karat gold, it's going to be easily dented. It's going to bend relatively easily. It's not going to be durable. And then the other reason, of course, is cost, because if you have something expensive like gold, you can add other less expensive stuff to it and make it less expensive. So that's an example of a solid homogeneous mixture, a solid solution. There are other alloys also, like brass, steel, those kinds of things where you're mixing metals together. All right, so then how about on the other side, a heterogeneous mixture? What do you got for those?
Pepper and salt.
Pepper and salt? Okay. So if you made a mixture of pepper and salt, you could see the pepper, you could see the salt, and you could physically separate them without changing those compounds, right? Now that's another kind of a interesting one, because I think that could actually go in either category depending on how you look at it. If you take some pepper, if you take like peppercorns, you know, like those round black peppercorns, and like big chunks of salt, and you put them together, it would definitely be heterogeneous because you know you could like pick out the different grains. But what if you ground those down to an extremely fine powder? It would start to be pretty homogeneous, right? Depending on how you were looking at it. So depending on that mixture, it could really go either way, and that's why these two definitions are not always perfectly fixed. Other definitions of heterogeneous mixtures? So anything that kind of has clearly separate domains, like oil and water, where you see the oil floating on top of the water, you can shake that up and you can homogenize it. You can make it look homogeneous for a second, but then it's going to separate right back out again. Remember that the separability does not define the difference between homogeneous and heterogeneous mixtures. So a lot of people sometimes will say homogeneous mixtures are hard to separate, heterogeneous mixtures are easy to separate. That is maybe true, like depending on the mixtures you pick, but that's not what actually defines those two things. You could have heterogeneous mixtures that are extremely difficult to separate, like, I don't know, sand in honey. I mean, that's a dumb mixture, but if you like put a bunch of sand in honey It would be pretty hard to get all the sand out of the honey, right? But that doesn't make it a different kind of a mixture, right? It still has like these solid sand particles and then the liquid honey part that you can see the different domains in. All mixtures can be physically separated. All pure substances cannot be physically separated. So that's the dividing line between those two. All right, so you think you can do this? Categorize some stuff? All right. So the book has some examples on some different methods of separation. You might want to look at those if you haven't seen them before. Physical methods of separation are things like distillation, filtration, decanting, that kind of stuff. Anything that you can separate, where you can separate a mixture without actually changing the components. How can you determine if something is a physical or a chemical change? So if you're talking about these separations or doing something like this to a substance, what are some signs that what you're doing is chemical and not physical? So maybe I'll help to look at an example here. So here's from the book. See if I can find it here. No, too far. All right, so here's a couple examples from the book that talk about physical versus chemical changes. So dry ice subliming, you take dry ice, which is a solid, carbon dioxide solid, you let it sit, it turns into carbon dioxide gas. That's a physical change. You dissolve sugar in water. So there's some sucrose dissolving in water. The solid sugar becomes dissolved or aqueous sugar. That's a physical change. You burn some propane gas. So you take propane gas, combine it with oxygen, make carbon dioxide and water. That is a chemical change. So how can we tell if we had some other process, what is the chemical change and what is not? What's the key difference there? Go ahead.
Chemical changes cause a change in the molecular level. Like
Yep.
they break apart or like they become something new.
So the chemicals change their identity and become something new. Okay. Anybody want to add to that? Okay.
I just want to like have the different form of the same substance.
What is?
A physical change.
A physical change, yeah, okay, so yeah, so a physical change, you might change the state of the substance. Do you always have to change the state of the substance in a physical change? You don't. Like a physical change can be as simple as separating two components of a mixture or tearing a large thing into smaller pieces. That's also a physical change. So the key here, as you can see here, and as you said, is the alteration of the chemical composition. If the chemical composition is altered, you've done a chemical change. If it is not, you've done a physical change. So you look for whether or not that substance has changed itself, changed its chemical form, its identity. Yeah. Good question. What do you think? Is rusting a chemical change? How do you know? Why?
Because it gives off heat
It gives off heat?
in the reaction.
That's true. What about like very slow rusting, like your car, where you wouldn't notice the heat? Is there another way that you could tell that it's a chemical change?
It changes from iron into iron oxide.
Changes from iron to iron oxide, so it's changing its composition. Yep. What if you didn't know? What if you didn't know the actual composition? What are some signs, just like visually looking at it, that would maybe hint at that this is a chemical change and not a physical change?
Well, it changes color.
Yeah, so color changes are generally, not always, but generally associated with chemical changes because how something absorbs light is usually a function of what type of stuff it is, like what it's made out of, what its structure is. And so if it changes its structure, it's probably going to absorb different kinds of light and therefore change its color. Now that's not always true. There are physical effects that change color, but it's a good like kind of general thing. Temperature changes are another one. If something changes temperature, that means that some types of energy is being exchanged, so either it heats up or cooled down. That is often associated with a chemical change. That also has some big exceptions, like making solutions. When you dissolve something in water, sometimes it gets hot or cold, and that is not a chemical change, that's a physical change, but the intermolecular forces are being messed with there. Anything else? What other types of things are associated with chemical or physical changes that you can think of? Yeah, you know.
Could we say texture?
A what?
Texture.
Texture. So texture could be very physical, right? Because you could like grind something up and change, or like polish it and change its texture. If it sort of changes it spontaneously without any of that, then that's probably more chemical, right? Yep, that makes sense. Gas evolution is another one, yeah.
Isn't like smell part of like chemical change?
Is what?
Isn't smell a good indicator of like chemical change?
It can be if there's a change in smell, yeah. If something smells a particular way and then it smells a different way, that's because some different chemicals are being given off. So yeah, that would be a good one too. Yep. I think that's probably good. So looking at those kinds of signs associated with those changes can help hint at whether it's a chemical or physical change. All right. So that's not my notes. That's not either. There we go. All right, so we talked about measurement and significant figures yesterday. You can practice some of those calculations in your homework and let me know if you have questions. But we want to talk a little bit about other types of units and converting between those units. Okay. So first, I'm going to assume that you all have plenty of experience with the metric system. But just to be clear, because we're talking about little tiny molecules, I can't find my table here. There it is. I'm going to put these into the notes. Oops. Oh, no, I don't want to do that. Okay, let's try that again. Well, I'll try to put it in the notes when I can. But anyway, this is in the book. You can find other tables like this as well. But here are some of the metric prefixes. You should know like these, pretty much. So make sure you know those. One way that I like to remember it is if you just remember the order, then you can remember the numbers that go along with it. So if you know that it goes, if you're going smaller, you got your meter, and then your milli, micro, nano, pico, and every one changes by 10 to the third, so it changes by 1,000. So if I said, how many nanometers are in a meter, you can go, all right, 3, 6, 9. So there's 10 to the 9th nanometers in a meter. The couple that don't quite follow that are the ones right around a meter, like deci and centi, which you've probably used before, but that's 10 and 100. So you should know those prefixes if you don't already. Working through the homework will help you a bit with that. Just to give you some scale as to where these numbers come from or what we use them for, the size of an atom changes from atom to atom. The size of an atom is on the order of 10 to the minus 10th meters. So that's right in the like hundreds of picometers, basically. So between pico and nano. You talk about nanoscience or nanochemistry, you're talking about things that are bigger than molecules but still very small. So things like proteins, very, very large molecules, very, very small particles, things that are kind of at the interface of molecular chemistry and what we would think of as more like bulk materials. So that's in that small side. On the big side, of course, we're familiar with kilo, and then you've got 1,000 more than that, 1,000 more than that. We won't use those quite as much because when we talk about large quantities of atoms, when we talk about things like moles, those are actually way beyond any of these. So we will mostly be using the smaller sizes of this and then up to about kilo, because like kilogram scale. Anything bigger than that is not something we deal with a whole lot. One place you'll see those larger prefixes, besides stuff like computers and data storage, is if you read stuff about climate change, about greenhouse gases, that kind of stuff, they often are measured in the megatons or gigatons of carbon dioxide. All right, so there's some prefixes. So I'll just make a note here that you should know everything from giga down to pico. Femtometers are smaller than an atom. Femtoseconds will often be used to describe the speed of chemical reactions, but we won't talk about that much in this class. All right, so let's work on some conversions here. We should mention also, you've probably heard it before, but density is the amount of matter in a given amount of space. We often express density in grams per milliliter or grams per cubic centimeter. And then we can use that as a conversion factor to convert between mass and volume domains. All right, so let's try this. A jet, large plane, is fueled with 173,231 liters of fuel. What is the mass in kilograms? Now you need a little bit more information to figure this out. One is the density of the fuel, which is 0.768 grams per cubic centimeter. And actually for this one, I think that's all we need. So generally with these types of problems, I'm sure you've done these before, we have to convert from one type of unit to another. In this class, the way that we'll set it up is you should always know the metric prefixes. We won't be given those. But any conversions between systems, like between the metric system and the US system, like centimeters to inches, or pounds to kilograms, or gallons to liters, that kind of stuff, those numbers will always be given. So you don't have to memorize those specific numbers, but you should know the metric prefixes. You should know how to go from, for instance, kilograms to grams, that kind of thing. So I'm going to show you how I do problems like this on this example, and then I'll give you some chance to practice with your own techniques. If you have done these in different ways that you like to do them and they work, stick with your own way. You don't have to do it my way. I just want to give you another option, a way that I think through problems like this. All right, so when I think of a problem like this, I like to make myself a little plan. Anytime we're doing these problems, we're converting from one unit to the other, especially like one like this, it's not immediately obvious what unit we're converting, or what path exactly we're taking to get from one unit to another. So I'm first going to look at the question and think about what am I given and what do I eventually want to get to. In this case, I'm given the volume of the fuel, the liters of fuel, and the question is asking me to find the mass in kilograms. So what I like to do is make like a starting point that I'm starting with liters, and at the end of this problem, I want to have kilograms. So I want to go from liters to kilograms. Then I'm going to look at my problem and think about, do I have a direct conversion here from liters to kilograms? Because that would make this really, really easy. We just do it and we're done. So do we have a direct conversion between liters and kilograms? In this case, we don't. We have a relationship between grams and cubic centimeters, but not liters to kilograms. So that means I'm going to have to take a couple more steps in my conversion to get from liters to kilograms. So we can go from both sides now and think about how to get where we need to go. One thing that seems obvious to me right away, or maybe not obvious, but one thing that I can see right away is that I'm given the density in grams and I'm ending in kilograms, and grams to kilograms, that's an easy conversion because that's just a factor of 1,000. So I might say, okay, from kilograms, I can probably, if I had grams, I could get to kilograms because I know there's 1,000 grams in 1 kilogram. So that's easy. Then looking at grams, I see, oh, well, I'm given the density, which relates mass and volume. So that's how I can get between the mass that I'm ending with and the volume that I'm starting with. Maybe I can use the density to do that. The density tells me how many grams are in a cubic centimeter. And now I'm getting closer because I've got a volume. How do we get from cubic centimeter to the liter or milliliter realm? It's what? Yeah, a cubic centimeter is a milliliter. So, oops. Those are the same. And so then now I'm getting really, really close because now I'm in milliliters and I know I can go between milliliters and liters just using my standard metric prefix. So 1,000 milliliters in 1 liter. All right, so it took a few steps, but we got there. We figured out how to go from liters to kilograms. So my next step then is to actually set up the mathematical conversion that's going to get me from liters to kilograms. But now that I've got my map set up, I should be able to follow the units and do this all in a fairly straightforward way. So I'm going to start with my initial number in liters, 173,231. 173 liters. And I'm going to take successive steps to convert this to different units. And when I do this, I like to write out all the units first before I put in the numbers. That helps me to make sure that I'm not flipping things. I find it to be a lot more confusing if I'm always thinking like, oh, do I multiply this or do I divide it? If you just follow the units, you don't have to make those decisions. Every time we multiply, we know that units that are on opposite sides of the fraction are going to cancel. So my liters, I can go from liters to milliliters by putting liters on the bottom, milliliters on top. Then I can go from milliliters to cubic centimeters, which I don't even really need to do because it's 1-to-1. Then cubic centimeters to grams. I'm just following my map up there, around the arrows around the bottom. And then finally, grams to kilograms. And so if I've done everything correctly, I've canceled liters, canceled milliliters, canceled cubic centimeters, canceled grams, and I'm left with kilograms, which is what the question asked for. So now all that's left is to fill in the numbers and actually do the calculation. So I know there are 1,000 milliliters in a liter. I know there is 1 cubic centimeter in a milliliter. The density tells us in this problem that we've got 0.763 grams in a cubic centimeter and 1,000 grams in a kilogram. By doing the units first, I am less likely to accidentally flip one of those fractions, because if I accidentally flip one of those fractions, then I'm going to be off by a bunch. So if I do all the units first and make sure that they all cancel properly and then put in the numbers, I have a little bit better chance of making sure everything ends up on the right side of the equation. All right, so then I'll get out my calculator. You can also notice here that there's a 1,000 on the top and a 1,000 on the bottom, so those will cancel each other out. So really I can just multiply by the density, so 173,231 times 0.763, 132,175. And then we should report that with the appropriate number of significant figures. So how many significant figures should we use here? We should use 3, and we'll talk about why that is in a second. So a couple ways we can write this. We can say 132,000. Oh, it's not 763, it's 768, but that's okay, we use 76. It's fine. Or really the best way to write this is in scientific notation. Why is scientific notation a better way to write that? It has to do with significant figures. So we talked yesterday a little bit about significant figures, but that number 132,000, it can be ambiguous whether or not those zeros are significant. Because normally we would say zeros after the numbers but before the decimal place are not significant unless we put a little decimal place behind it to show that they're all meant to be significant. But that can be ambiguous because you don't know. Maybe you're just missing a little dot. So if you really care about reporting things to the correct number of significant figures, you've got to use scientific notation. That's the only way that we know for sure there are 3 significant figures in that answer and not 4 or 5 or 6. It also solves that problem of, let's say our answer is actually 132,000, but we want to report 4 or 5 significant figures. There's no way of specifying that those zeros in the middle are going to be significant unless we use scientific notation. So if the significant figures are important, you really got to use scientific notation. So another question then, going back to our conversions, the number we started with, the 173,231, that has, 6 significant figures, right? And then the density has 3 significant figures. What about those 1,000s? Why didn't that come into significant figures here? Ideas? Yeah. There's no decimal point, but how many significant figures are in that 1,000 ml per liter? Any idea? It's kind of a trick question. Yeah, it's actually infinite. So what's happening here is we're thinking about measured versus exact quantities. So an example of an exact quantity is 1,000 milliliters in a liter. There are exactly 1,000 milliliters in a liter by definition. Not 1,000.0 or 1,000.00 or whatever, exactly 1,000. So that means that exact numbers like that have infinite significant figures. You can assume there is as much significance as you want because they are exact. They're a count, they're a definition. any counting number like that is an exact quantity and not a measured quantity. So other examples like that. Let's say we're like doing some conversion about people in the class, and there's 22 students per class. So 22 students per class is an exact number, not a measured number. There's not 22.0 students per class. We're not talking about fractions of students. It's an exact count, and that makes it an exact number. Same thing with all the conversions in the metric system. Conversions in the US system as well, like there's exactly 12 inches in a foot by definition, not 12.0 or 12.1. So if you're converting between inches and feet, you don't say that 12 has two significant figures. You say 12 has infinite significant figures and use one of the measured numbers for your actual count of significant figures. So measured numbers, generally with a couple exceptions, the ones that go between the systems are usually measured numbers. But anything with a decimal place, you know, like a density like 0.763 grams per cubic centimeter, are going to be measured numbers. Quantities that you're given at the beginning of a problem are generally measured numbers. A couple just weird exceptions there. There are exactly 2.52 centimeters in an inch. So that's actually an exact number, even though it looks like a decimal. But that's why we don't use those 1000s to help to calculate that significance. All right, let's try another one. Oops. So we're going to do a fuel efficiency conversion. Convert 22 kilometers per liter to miles per gallon. And I'm going to give you a number for that because I told you whenever we go between the systems, I will give you those numbers. So there are hold on, there we go. Oh, 2.54. I misspoke before. I'm sorry. There are 2.54 centimeters in an inch. Actually, wait, that's going to be really hard. Let's try a different one. I'll give you a little bit easier time with this. There are 1 kilometer is 0.62137 miles. All right. And one liter is 1.0567 quarts. And there are 4 quarts exactly in 1 gallon. Okay, that should be all the information you need. See if you can convert that fuel efficiency from kilometers per liter to miles per gallon. Yeah, give you another minute or so to work on this one. Don't worry if you haven't completed it when we start going over it, but
Should we treat 22 as an example?
no. That would be a measure number. All right. Should we try it? So what'd you get? I don't actually know the answer, but what did you all get? You wanna? 52? 50 something? 52? 52? 52? Okay. Let's see if we get that. So the thing that's a little bit different about this one compared to the previous example is we actually have to convert the top unit and the bottom unit of the fraction. So that first number is 22 kilometers per liter, which we could also write as 22 km per 1 liter, like that. And so we've got to convert that top from kilometers to miles, and we got to convert the bottom from liters to gallons. So we've kind of got two different conversions going on. We can do them together. All we have to do is switch the units. So when we, like in the previous example, we always put the unit we wanted to get rid of on the bottom and the new unit on the top of the fraction. If we're trying to do that to the bottom of the fraction, we're just going to flip that. So the old unit goes on top, the new unit goes on the bottom, so that the old units still cancel. We can still set up our plan here if we need to. So in this case, we've kind of got two plans. We're going to go from kilometers to miles, and we have a direct conversion for that first number. So we don't need to take a bunch of steps. It's just kilometers to miles. And then we're also going to convert liters to gallons. In this case, we don't have that conversion. We have liters to quarts, and we have quarts to gallons. So we're going to have to take an extra step there to get liters to quarts and then quarts to gallons. Move this down a little bit. Okay. So then actually completing this, once again, I'm going to start with my units and then fill in the numbers. It doesn't matter what order we do things in, because you can multiply in whatever order you want. Let's do the top first. So I'm going to put kilometers on the bottom and miles on top. And that should convert from kilometers to miles. That's just the one-step thing. And then I've got to go liters to quarts to gallons. So liters to quarts, since liters is on the bottom, I'm going to cancel liters by putting it on top and then having quarts on the bottoms. And then quarts to gallons. So just let's check to make sure everything cancels the way it's supposed to. Kilometers cancel with kilometers to leave miles. Liters cancels with liters. Quarts cancels with quarts. So the only ones that are left are miles on the top and gallons on the bottom, which is exactly what we want. So now we can fill in our numbers. Our conversion factors over here on the right tell us that there are 0.62137 miles in a kilometer, 1.0567 quarts in a liter, and 4 quarts in a gallon. All right, all that's left is to calculate that. So 22 times 0.62137 divided by 1.0567 times 4 is 51.7, which we're going to convert to, or we're going to round to 52 miles per gallon. All right, nice job. So there was a question about that initial 22. Is that a measured number or an exact number. In this case, it's measured. It's the quantity. It's the kilometers per liter, the fuel efficiency that's measured. But one thing that kind of brought to mind for me is when we think about these ideas of precision and measurement precision and significant figures, a lot of the numbers that we encounter in our lives are not as precise as the numbers that we deal with in the lab. So when like fuel efficiency is reported in a car, it's generally reported to two significant figures. So like 22 kilometers per liter, 52 miles per gallon, which tells you there should be about a plus or minus 1 error bar in that. With medication, so if you take like a pill, you look at the pill and it says 150 milligrams or 250 milligrams of ibuprofen, right? You've seen stuff like that. So that's plus or minus what? If it's reported as 250 milligrams, what's the actual plus or minus there, do you think? I mean, we can just guess, but we don't know for sure. But what would you think?
A milligram.
What?
A milligram.
So it could be a milligram. It depends on how that's written. If it's written... If it's written 250 milligrams, and it's just written like that, how many significant figures do we have to assume is there? Just 2, right? Only the 2 and the 5 are significant. So that means that really that number should be between 240 and 260, because the 0 we're saying is not significant. So we would expect something reported in this range to actually mean somewhere between 240 and 260, which is a range of about 20 milligrams, or just under 10%. So when so I saw a thing in an article saying something like, beware of your drugs because beware of your prescription drugs or your generic drugs because they can be as much as 10% off in composition. But by law, that's because of the significance of the measurement. We're saying that measurement doesn't actually need to be any more precise than that. That's just how it works. If we wanted that third digit of significance, then that would require a whole different set of regulations. All right, good with that? So the last thing we're going to do today is temperature conversions. We're going to use 3 temperature scales in this class. You've probably seen them before. Degrees Celsius, degrees Fahrenheit, and kelvins. We'll use degrees Celsius for most of our work in the lab, for most of our measurements. We'll use degrees Fahrenheit just because that's the temperature that we most often are familiar with growing up. If you grew up in this country, we tend to measure our air temperature and stuff like that in degrees Fahrenheit, so we have a good reference for what that is. So we'll be converting between those. And then, does anybody know what we use kelvins for as a scale? Why is that an important scale in chemistry? There's a couple of reasons, but yeah, go ahead. This one?
To measure absolute values, absolute zero.
So Kelvin is a scale that goes down to absolute 0. And why is that important? Why is it important to have a scale like that? Guesses?
Because nothing can go lower than absolute 0.
Nothing can go lower than 0. And so that makes Kelvin a useful scale when we do calculations. Because it can't be negative. If you think about all the other units we use, like grams, meters, whatever, they never go negative. You don't have negative meters, right? Unless you're talking about, vectors or something going the wrong way. But in general, you're talking about a quantity that comes up from 0. And so when we do calculations with temperature, like gas law calculations, stuff like that, you need to have a scale that ends at 0 because a negative number would kind of screw everything else up. So we use Kelvin for that because Kelvin, you'll notice there's not a little degree sign. Kelvin is actually a unit. So when we say 273 kelvins, we say kelvins because it's actually like saying grams or meters. It's a unit. That's lowercase k kelvins. The unit itself is an uppercase k. So to convert between these 3 scales, if we kind of take a look at what those scales look like all together, I like these types of pictures that show this. If we look at these three thermometers, you can see that you've got absolute 0 at the very bottom, which for Kelvin is 0, for Celsius minus 273, and for Fahrenheit minus 459. Then you've got the freezing temperature of water, which is 0 degrees C, 273 K, or 32 degrees Fahrenheit. And then up to the boiling point of water at 100 degrees C, or 212 Fahrenheit, or 373 K. By putting the scales together, you can notice a couple things. One, there are more degrees in between the Fahrenheit, on the Fahrenheit scale between the boiling and freezing point of water. What does that tell you about the relative size of the degree between the Celsius and Fahrenheit scales? But there is a difference. So which one has smaller degrees, Fahrenheit or Celsius? Fahrenheit has smaller degrees. You see that? Because there's more of them in between the same range of temperatures. So the Fahrenheit degrees are smaller. There's also an offset that you see because water is freezing at 0 degrees C, but 32 degrees F. So that means that when we convert between those temperature scales, specifically between Celsius and Fahrenheit, we have to actually, we can't just like do a nice conversion like we did with the other ones because it's not a purely multiplicative conversion. We have to multiply to change the degree size, but we also have to add or subtract to change the start point. So for these conversions, you actually have to memorize a couple simple equations. And they look like this. You can get the degrees Celsius by taking the degrees Fahrenheit and subtracting 32, and then dividing by 1.8. And it's really important that you do that subtraction first. So you've got to be careful on a calculator, especially a newer, like a graphing calculator. Graphing calculators follow the order of operations. So if you just type like 100 minus 32 divided by 1.8, it's going to do the division first and then the subtraction, and you're going to get the wrong answer. So you've got to make sure to either put the parentheses in or just hit enter in between the subtraction and the division so that you're not dividing before subtracting. The easiest thing, I think, is to just remember one of these equations because you can always get the other just from algebraic rearrangement. So if we multiply both sides by 1.8 and then add 32, we get the complementary equation, which is that the degrees Fahrenheit is 1.8 times the degrees Celsius, and then add 32. And in this case, we would follow the order of operations. We would just multiply first. I don't think there's a need to memorize both of those equations because, again, you can always rearrange one to make the other one. And then the Celsius or the Kelvin conversion is probably the easiest because Kelvins are the same size as Celsius degrees. So the only difference between the Kelvin scale and the Celsius scale is where you start. So instead of starting at 0 in Kelvin, you start at 273 for Celsius. So that means that your Kelvins are going to be your degrees Celsius plus 273. And if you need more significant figures, it's actually 273.15. That 32 is considered an exact number, as is the 1.8 because it's actually a fraction, 9 over 5. The 273.15, I don't know if that's an exact number or not. Let's see if we can find a better. Yeah, that's all they give here. So I don't know. We can look that up. So that's how you convert from one temperature scale to another. Okay. So, questions about that so far? Okay. Thinking about that pretty much takes care of chapter 1. If we look at the key learning outcomes at the end of the chapter, the things that you should be able to do, you should be able to determine chemical, physical changes, properties, states of matter, right? Categorizing matter. Make sure you can convert between temperature scales, calculating density and using density to do conversions, Reporting scientific measurements to the correct digit of uncertainty. We worked on that yesterday, and then we did some calculations like that today, and significant figures. And then conversion factors. So the couple things in the book that you are not responsible for from chapter 1. One would be memorizing conversion factors between systems. So like how many liters are in a quart, or how many miles are in a kilometer. You don't need to know those numbers. You'll always be given those numbers. So you don't need to be able to do that. And then there's a thing at the end of the chapter that says solving problems involving equations, which is kind of a weird way of wording it, but basically it's like they do a lot of problems with density where you actually have to calculate like the volume of a sphere, and then use that to like figure out the density. You don't need to remember those equations from high school geometry or whenever you learned those. Like what's the volume of a sphere, what's the volume of a cylinder or a cube or whatever. You don't need to have those equations memorized. They will show up in your homework, but you can just look those up if you need them. So if you need to calculate volume, you can calculate volume. You can look up how to calculate volume. You don't need to memorize those equations. All right. Sound good? Everybody feels all right about that? Okay, so we'll stop here. We'll head downstairs. I believe it's room 131, which is right at the bottom of the stairs, of the angled stairway. And I will bring the group activities, and we'll get some practice on some of these problems. We start at 9:30 down there, by the way, so if you need to grab a snack or a bathroom or something, you have a little time.